Thank you, Chairman. I'm Nozomi Sugiura, working for JAMSTEC. And title of my talk is discretization of Onsager-Machlup functional. It's a word from physics community. It actually is a model error term. And my main claim is that, first of all, we are solving this nonlinear smoothing problem, dx equal fx dt plus sigma dw. W is a Wiener process, and x is state variable, and f is some nonlinear tendency function. And we can discretize this SDE like this. Time step is delta t, and at this stage we use Euler-Maruyama scheme for time discretization. And this one is normally distributed random number. And as a smoothing problem, we have XB, background initial condition, and observation. And for simplicity, we just think about easy covariance. And my claim is that the proper setting for the minimization of cost function for minimization is like this. This term is this one is background. This one is observational term, and this term is model error term. But my claim is that we need divergence f. Always we need this. This is my main point. But this divergence term should be excluded in Monte Carlo method. It's very tricky, but it's true. First of all, I call this model error term prior, and prior has two meanings. We can assign one of the following prior probabilities, and one prior is probability for rough, that means zigzag path in Ito form. It's a stochastic integral, so we have to be we have to choose one of Ito or Stratonovich integral, and it's a Ito form. In this case, you don't need divergence term, and another probability is that for smooth tube, it's not a probability of for a path, but it's a probability of a neighboring path like this. X is neighboring path of smooth tube chi. For chi, we can assign this probability. It has a divergence term. It is proved a long time ago, 1981. And we can solve that nonlinear smoothing problem by two methods. One is MCMC, Markov chain Monte Carlo. That samples pass according to the posterior distribution, like this. You can use gradient of logarithm of posterior and add perturbation. It is also called Metropolis-adjusted Langevin algorithm because it has a rejection step for adjustment, Metropolis rejection step. In this case, you can get an ensemble path according to posterior probability. And second one is 4D bar. 4D bar 6, the most probable tube, chi, by iterating. It's a smooth tube, chi, iterating, like this. It's just a gradient method. Then you can get map estimate for the tubes. So we are going to test 4 discretization schemes for prior, and this prior has another name called Onsager-Machlup functional, named after Lars Onsager. And our discretization schemes are one, Euler. Euler is f is taken at n-1 and don't use divergence. And Euler with divergence ed is f is taken at n-1, but also we add divergence. Third one is trapezoidal. That is, f is taken at the middle point and without divergence term. And fourth one is trapezoidal with divergence TD. It has a main point F and divergence. We need also reference solution without using prior probability. We can solve it by particle smoother. Particle smoother is very easy for small problems. Generate samples of initial and model error and integrate m copies of model using that error and obtain Monte Carlo approximation of the prior distribution. This one, delta, but reweight it according to Bayes' theorem. In this case, we suppose observation is only at the end of the window, and Bayes' theorem, and reweight, and you can get the posterior. This does not need prior, but need huge particles, of course. And the first example is hyperbolic model, one-dimensional model. It is proposed by down, and it is dx tau hyperbolic tangent dt plus dw. And we have observation at the end of the window, t equal 5, and value is 1.5. And in this case, divergence f is second, hyperbolic second, which impose penalty for small x. We're going to solve this particles with particle smoother and MCMC and 4D bar and confirm which one is proper scheme. Here's the result for MCMC. This one is a reference solution by particle smoother, and time goes this way, and this is state variable, one-dimensional, and this is a probability density of a path normalized on each time slice. You can see map estimate is almost straight line. If you solve this with E or TD, Euler or trapezoidal with divergence, you can get almost right answer. But if you use ED or T, obviously they are wrong. This is the same thing, but just mean orbits, expected path. You can see that particle smoother black cube, black one is coincide with E or TD. They are right answer. But T or ED are not right. But if you solve this by 4D bar, right answer is provided by ED or TD, which means we always need divergence term. Second example is Lessler model, three-dimensional, and the setting is almost the same. If you see the result of MCMC, you can see that this time also E and TD of a proper expected path. But if you solve by 4D bar, map estimate is proper map estimate is provided by ED or TD, which have divergence term. Summary is that we examine the discretization schemes of OM functional and consistent. Actually, it's consistent with past literature. Following discretization are correct. For MCMC, Euler without divergence or trapezoidal with divergence is true, right? And for map estimate, Euler with divergence or trapezoidal with divergence are right. So I recap the main claim, main claim that for nonlinear smoothing problem, this one, proper setting of cost function, one of the proper setting is like this. Divergence is needed. But for MCMC, we don't need divergence if you use Euler discretization. That's it.